Welcome back to Inorganic Chemistry. In this lecture we're going to start chapter 12, looking at the reactions of coordination compounds. And in particular, actually we're going to step back a little bit and review how to make coordination complexes from chapter 10. And we'll see that this is significant because we actually have to do ligand substitution to form these complexes. And so then we'll look in chapter 12 at the mechanisms of ligand substitution. We'll look first at octahedral complexes and how the d-electron configuration of the complex can affect the mechanism. And then we'll also look at squared planar complexes and their pseudo-first order kinetics and also the trans effect. And in the final part of these series of lectures we'll look at electron transfer reactions of coordination complexes. So to form a coordination compound, again, these are metal ligand bond forming reactions, which are actually, Lewis acid. The metal is a Lewis acid, the ligand is a Lewis base, and so we're making an adduct or complex, Lewis acid base complex. And so this equilibrium is a complex forming equilibrium. And we actually get stepwise formation. We make one metal bond, a second, a third, and so on until we get to a total of usually 6 ligands coordinating to the metal. And so the total overall equilibrium constant for this formation of the 6-coordinate complex is a product of the equilibrium constants for each step along the way. And in older textbooks, this total equilibrium constant is called beta. In newer ones, we maybe just refer to it as Kf, the formation constant. And it's going to follow thermodynamic laws and help us understand the thermodynamic stability of a particular complex. So what are some factors that will affect this equilibrium? One is statistics. So again, let's step back a little bit and recognize in the gas phase this would be the case. Usually though we're working in an aqueous solution. And so we have the metal ion in water, which is the same as a metal complex of water, usually 6-coordinate. And so to add the ligand of interest, we actually have to substitute out one of the water molecules. See, here we had 6 water molecules. Now here as the product we have 5 water molecules according to the metal and 1 ligand of interest, and then we displaced one of the water molecules. So this is our first step, K1 forward, or negative K1, the reverse, or K of negative 1, the reverse reaction. Yeah, actually this should be K of negative 1. K, that's the rate constant of the reverse reaction. It is not equal to the negative of the rate constant of the forward reaction. However, we do know that the equilibrium constant is equal to the ratio of the forward and reverse rate constants. So in the second step we have a similar situation. The ligand is going to displace one of the water molecules so that there's only 4 water molecules remaining. And so the equilibrium constant for the second step is K, the forward constant, rate constant for the second step, and the rate constant for the reverse step. And we know that the rate of this happening is going to be more than the rate of this happening. because here we have 5 water ligands to displace, whereas here we have 6. If we displace the ligand with the ligand, a self-exchange, or actually back here we didn't progress at all. So we have 5 out of 6 chances of getting it right, and so statistically the rate of the first forward reaction must be greater than the rate of the forward second reaction. Similarly, going back, reverse reaction, here we have 2 chances for water to displace the ligand to go back to the starting complex here. And here we have 1 chance for water to displace the ligand to come back to the starting complex. So in the reverse direction, K negative 2 is twice as large as K of negative 1. So putting all of this together, we can substitute in and say that the equilibrium constant for the first step is 12/5 of the equilibrium constant for the second step. This first step has to be a large equilibrium constant just based on the chances of colliding and displacing one of those ligands. Okay, well, that's just for math. Let's do some chemistry. Again, this is a Lewis acid-base reaction. So metal ion acidity. The metal ion is the Lewis acid. If it is small ion, so small radius, larger, I guess I should say smaller ion, larger ionic charge. So is it +3 or +2? Both of these factors will increase the acidity of the metal ion and therefore increase the equilibrium constant to form the complex. We could also then look at the ligand side of the equation and how basic is the Lewis base of the ligand. So here we have an example of water ligand bonded to the nickel ion and ammonia coming in to react, and we know ammonia is a stronger base than water, and so we would predict that this equilibrium constant is greater than 1, and sure enough, at 25 degrees, the equilibrium constant for this reaction is approximately equal to 1 times 10 to the 9th. So the formation of this complex as opposed to the water complex is highly favored, and that tracks with what we'd expect because of the base strength of the ligands. And finally, we can look at entropy affecting the thermodynamics. In particular, a particular type of interaction here is called the chelate effect. And a chelate is a bi- or multidentate ligand. And we've talked about the teeth of the ligand, the points at which the ligand can bind to the metal. So for example, this is ethylene diamine, and its abbreviation is just EN, ethylene diamine, and you see that there on each end of this molecule is a nitrogen with a lone pair. So there's 2 teeth. It's a bidentate ligand. It can chelate. Chelate means to bite. It can bite the metal and to form the complex here. And thermodynamically, we're making a nickel 2+ nitrogen lone pair Lewis acid adduct in both cases, with ethylene diamine and just plain ammonia. So delta H is probably about the same. Where we are. Delta H is about the same for both of these reactions. What's happening then on the entropy side, we see that here we go from 7 molecules to 7 molecules. Here we go from 4 molecules total to 7 molecules. So we increase the number of molecules in the product, which means we increase the amount of possible arrangements, which means we've increased the entropy. So the second reaction with the ethylene diamine increases entropy. If entropy increases, change in entropy is positive, then delta G gets more negative. Delta G more negative is exergonic. It's more favored. More exergonic. The products are more favored, and so we would expect the Kf for this reaction to be larger, and indeed, again at 25 degrees, and these are so different, we're going to do the log. We've seen this one already, actually. Log of Kf. We said it was about 1 times 10 to the negative, or 1 times 10 to the ninth, and I have a value 8.61, whereas for the ethylene diamine, the equilibrium constant, the log of the equilibrium constant, is 18.28. So it's a factor of 10 tens more favored reaction. And this is called the chelate effect. And this happens whenever you have a multidentate ligand that can bind to the metal. And ideally, okay, we just went over the entropy. Delta G is more negative when delta S is more positive, and therefore if this is more negative, our log of our equilibrium constant is more positive. Ideal bite size. So depending on the metal ion size and charge, you either would prefer a 5-membered ring or a 6-membered metallocycle. And we see this is actually very similar to what we saw in organic chemistry. Cyclopentane, cyclohexane are more stable than cyclobutane or cycloheptane. And so it's similar considerations in terms of bond angles and such. So we call that the ideal bite size. We can keep doing this as bidentate. We could make a tridentate ligand, which would have even greater chelate effect. And if we make the multidentate ligand into a ring, we have a macrocycle. So the multidentate ligand actually surrounds the metal, and here is probably one of the most important examples of a macrocycle. We have an iron ion, and it's bound at 4 points, 4 nitrogen lone pairs coming in a ring here, and this ring is fairly rigid with all this aromaticity, and then it has these different substituents off of it. This is the molecule heme B, or iron protoporphyrin 9, which is the most important oxygen carrier molecule in the hemoglobin protein in your red blood cells. And this part of the structure here is very stable. We saw that Kf is we would predict to be very large because we have multidentate and this surrounding structure here, so it's very hard for other ligands to come in here. Now, binding axially is open, and that's actually the important part. The dioxygen is going to come in and bind at this axial position, and the other end of the iron is bound to the protein. So the iron is octahedrally coordinated in the hemoglobin. Okay, so that concludes our discussion of the thermodynamics of coordination complex formations. and then that will help us understand the reactions of coordination compounds. In our next lecture, we'll look at the kinetics, begin to look at the kinetics of coordination compound complex reactions.